Wow. 130 seconds, 0.3 milliseconds. Amazing. We are gonna check. Okay, if we check lap times for Laguna Seca, the new Tesla made it in around 130. So that would be like the Huracan. And Elon says you could remove 3 more seconds. That would be 127. That's like a McLaren Senna, something like that. Amazing. I mean, amazing times.
We took the latest plaid out to his Laguna Seca on Sunday. It got a minute 30, and we think probably there's another 3 seconds or more to take off that time. So we're confident the Model S plaid will achieve the best track time of any production vehicle ever, of any kind, 2-door or otherwise.
Okay, so I see something that to me comes to mind. I don't really know how a battery works, but you see that it goes from the cathode to the anode, and when you charge it, it goes the other way around, anode to the cathode. Couldn't you just do like a donut kind of shape battery, so that when it goes into the anode, it's already the cathode for the next battery, and infinite, let's say, and you do a donut. Imagine you have 5 of those interconnected, so you are loading one. When you use it, you load the next one, and infinite battery. That would be cool, but I suppose those get used because the moment the electrons get to the anode, basically they will be used or consumed by the power of the engine, and in that case you need to bring new electrons into the battery. But that's just my thought. I thought it was very nice to have a nice explanation like this. Simple. Okay, I'll continue.
And when we look at what's happened today, at least in our products, we've moved from the 18650 form factor to the 2170 form factor through great collaboration with our partners, Panasonic, new partners like LG and CATL, and probably others in the future.
Yeah. Actually, so a slight note on why is the one called the 18650, although not on the slide, versus the 2170, is that the first 2 digits refer to the diameter, and the second 2 digits refer to the length. So that helps explain why are these weird, what's up with these weird numbers.
Okay, so I'm reloading to update the situation right now. The stock market just opened a day after battery day, so the day after battery day itself. So it's the 23rd, and I don't know why it's not loading. Okay, so now it's working. So yesterday we went down after market minus 7%, all the way to 390 or something like that. 380, I think I saw at one point. And I mean, we can see it here, but for some reason it doesn't show me the, oh, now it's showing me that, and we can see some green volume, and as you can see we reached 391. So we just open, and we can see we're in the 5 minutes. We're gonna change to 1 minute. So far, down movement directly. So we're gonna sell a few of the shares in case we drop, since lately we've been going down a lot. So Tesla, and we're gonna sell. Most likely it's gonna go up. So we'll sell 10 at 425.01, and we'll check more or less. That's what we bought yesterday at 430 or something like that, average price more or less. So we're losing $5 per share. That's $50. But we might recover it recovers later on through the day. Oh, but now we are already 409. Incredible. Let me see. That was a big drop, or this was not updated properly. It was showing 424, 425, but now seems to be going up. So if that's the case, we'll put a higher price. So we can put 450.01. That was our target, our highest target yesterday. And I hope I put it correctly, because, okay, many things are getting bought. And we close this. So we bought several things at opening. That's opening. That was yesterday, 22nd. And we bought some Nordstrom zeros, Intel plaque, Corvo, Fastly, and Dropbox. So let's see. So far the entire portfolio is going down. One of the good things is to check the portfolio in the hype moment, which is when you open, see if there's something big going on that might help you to reduce some losses. At the moment, nothing is very significant, 3%, 4%, that's okay. And here we see outstanding orders, and here what I do the Tsla, so I can easily or quickly access them, and I can put them here. Okay, so we are in this small range, way below where we want it to be, and so far doesn't seem to be deciding whether to go up or down. It's moving sideways. So we'll wait a little bit more. See, you see now it just changed, change its mind. Now this one, it open. If it opens, that means it's going to drop more, but it's still creating this doji. Sorry? Elon, what do you think? After what you told us yesterday, the reaction from everyone, the market, is this something you were expecting? I mean, based on your tweet, I kind of knew. I still thought there might be some push up, but no, it just didn't happen. So look, it opened, so that's going to mean it's going to drop. So we might as well just sell a few more, sell some shares at 405. We'll do that. We'll change to 405, 80, 75. But that was too late. I can see already. 404.75. Mostly just to cover ourselves. Oh, now it's dropping big time. And 403. So now we have a hype point, and normally at this point is when I check the portfolio again, and that's because normally at this hour, 15 minutes after opening, 10 to 15 minutes, there's a big hype in the market. It can go up or down depending on where the markets are going, but as so far I see a lot of green. This column here shows you today, what each stock is doing today, percentual, and by amount. So that's good. That's good. I think yesterday we bought more, but yesterday it dropped. So now it's recovering. And we have some budget here to buy new stuff, which is what we just sold from Tesla. So we might be able to buy it back at a lower price. And my daughter is there making fun of me at a lower price. And as long as this is open, and that's a good sign, we could try to sell more since it's so open. Now we're at 402. If we sell more, what we'll need to do is calculate. Oh look, now it went up to 404, 403. So if we sell at 3.99, that would be 1% less, and if we divide by another 3.95, then yeah, seems to want to continue to go down. You look at for 1 millisecond that it was going to recover, but this is open. You see the height of this square or rectangle shows it's bigger than the previous one, shows you that there's more momentum on the downside. So we can sell a few more, I think. So we'll do that. Tesla. Sell. We can sell 20 more, since it looks like it really wants to go down. 402, and now it's trading in the 400s. So if I go like this, close, and go here, I should see. Oh, it looked like it just went through it. It went through or not? Tesla transactions. Now I check the transactions. Tesla, come on. Okay, we'll open it again. It looks like the computer needs a bit of reboot or something. But I don't see any Tesla sell here. Is sold. So normally I just, okay, here you see it. So 402, but we're at the 401 now level. But look, I see some recovery. I like that. I don't know if that's gonna happen, but if that's the case, I don't want to sell. So I'm gonna put 003. I mean, we can even put 050 again. Sorry, 450 at the moment until we decide whether we sell or not. You see this green? Look at that. That's turning around. That's turning around. That's good. We're at minus 530%, and that's already a good sign of recovery. It doesn't mean it will. It doesn't mean it will. You see here it started recovering and then it dropped, and finally it starts dropping. So falling. But look at that. We're at minus 495 already. So that's really good. It's going up. It's going up. We just sold 10 shares for nothing. I mean, we could recover them, but since the situation is very shaky, I think we'll lose on that one, on those ones, and that's it. I don't see, there will be other opportunities most likely if the trend changes to recover the money basically. So at the moment there's no trend, it's flat. The 200 moving average dictates more or less the trend. If the 5 and 13 go above the 200 moving average, that will start making a change into the trend on the up direction.
This was a evolutionary step going from 1865 to 2170, bringing 50% more energy into the cell. But when we look to the ideal...
He just said one very important thing, bringing 50% more energy into the cell. That's not power, that's energy, voltage. But if you go through the entire presentation, you're going to see many very important points. I mean, they do many tweaks to the battery in order to the battery and also the entire factory to make, and even the mining, they are touching every single step of the process, retweaking it to make it better and more efficient. That's going to take a long time. They explain why. And so in the long run, it just shows you that Tesla will be unbeatable, basically. I mean, they are so ahead of the competition that it's unbelievable. And here we will see that they touch 5 very important steps of the process that will increase energy, capacity, power, everything is going to be better. Weight, lighter weight with more capacity. They're even going to use the structure of the cell to be part of the structure of the car, like they do with the wings in an airplane, with the tank gas of the airplane.
That's what these T-shirts mean, but it's very esoteric. It's like nobody could figure it out. But
yeah, we basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see. With simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like basically the distance that electron has to travel, you know, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. Elaborate on that a bit. It's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yes.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and it really slows down the rate of production. And then
so here we can see, okay, so we'll gain 5 times more energy, that's the voltage, 16 times the range, and 6 times the power. 6 times the power, that's amazing.
But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change.
Okay, just so you understand, only talking about the cell itself, that's gonna give us a 14% reduction in dollar per kilowatt hour, okay, just this. Then there's, as I just said, there's 5 steps into the process which are going to give at around 57% improvement in the entire battery system. So now they're going to start talking about the cell factory.
If you do scale it up,
yeah,
what you saw before becomes this.
yeah,
You can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy and a massive reduction in investment. But as Elon was saying, simple is hard.
Yeah.
Basically, what they're doing is they're reducing everything. They're simplifying everything. They make it a lot more simple. Here's my daughter, actually. That wants to say hello, I suppose. Hello. So, what they're doing, it's reducing the steps within the factory, and they're using always techniques from other industries like bottling to create faster way to manufacture the batteries. So
Yeah, I mean, to be clear, I would like not say that right now it's just totally working. It's close to working, but it's not even now at the pilot plant level. It is close to working. Well, it's fair to say it does work, but with not a high yield.
Yeah,
So
we're still ironing out the kinks, but we made tens of thousands of cells, thousands of kilometers of electrode. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way.
Yeah.
I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there.
So as they're saying, it's not yet working. It's almost there, but it's 4th generation of trial and error until they get to the final one that will be working, obviously.
So this is pretty profound. You know, it's like I would actually not have thought this was possible several years ago. That we could actually get to terawatt-hour scale in less space than what we currently envision for doing 150 gigawatt hours.
Yes, simpler accelerates terawatt-hour scale, and that's what we need to do to accelerate our mission. And you know, as Elon said, we're going to try to even improve on this as we push towards our goals, which are.
Yeah. So this is just for. This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL. And so this is 100 gigawatt hours supplemental to what we buy from suppliers. Yeah, essentially, this does like reduce our weighted average cost of a cell because it allows us to make a lot more cars and a lot more stationary storage.
So basically, if I understood correctly, they're going to produce a lot more batteries or energy with a lot less capacity. So that's basically part of the plan, okay?
By 2030. And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level.
But wait, there's more.
But wait, there's more, okay? So basically, if I go back, the battery cell is going to produce 14% improvement. The factory production is going to produce 18% improvement. And now we're talking about the anode materials, okay? So a bit into the mining.
But wait, there's more.
But wait, there's more. So we have a manufacturing system, we've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand.
Yeah. Sand is silicon dioxide.
Yeah. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. So why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium. And basically all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand.
Yep.
Okay, a little pause back to trading. As we were watching the videos, here the stock went down, fell down. but it recovered back to more or less the 403 where we sold 10 shares, and it looks like now it's gapping out between the two, the signal and the MACD. That means it's gaining momentum on the way up, and we'll see where that goes from there. So going back to battery day, they're explaining that they're going to use silicon, and with that they can increase the range by 20%. Silicon basically is sand, and is the second most found element in Earth. Sorry, my kids are here. And so imagine, by just using silicon, you increase range by 20%. And they say, why aren't the other people using it? Basically, because it expands 4 times the volume. And that's a problem, because with the electrons, you need to have everything, all the electrons in order, organized. And for that, you use the cobalt. So, and they want to eliminate fully cobalt, so they have to find a solution to make this work with silicon and combine it with other materials that will be doing the work of the cobalt, which is organizing. And they do a comparison to shelves in a bookshelf, so that to organize the electrons.
Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And
so with the anode reduction, they gain 5% more. So far we're at 37%, 14, 18, 5%.
let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves, where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. Cobalt is
Yeah, sorry, I was going to say, it's tough to exactly figure out what the right analogy is to explain cathode and anode, but a bookshelf is probably a pretty good one, in the sense that you need a stable structure to contain the ions. So you want a structure that does not crumble or get gooey, or basically that holds its shape, both the cathode and the anode. As you're moving these ions back and forth, it needs to retain its structure. So if it doesn't retain its structure, then you lose cycle life and your battery capacity drops very quickly.
Okay, that was a very good explanation from Elon, and I realized I messed up. I was talking before about the anode and talking about the analogy with the bookshelves, but that's for the cathode. Okay, so that's clarified right now.
But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode dollar per kilowatt.
And these things just grew up as they're just kind of like legacy things that it's like how it was done before. And then they connected the dots, but really didn't think of the whole thing from like a first principle standpoint, saying how do we get from the nickel ore in the ground to the finished nickel product for a battery. And so we've looked at the entire value chain and said, how can we make this as simple as possible?
And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and 0 wastewater. Much more scalable solution.
Yeah.
They're like taking all the details in the entire process, and they're reducing investment, the cost, and waste. So it's a win-win-win situation.
And now that we have this process, obviously we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost.
Yeah, I mean,
On that note, the way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode.
As you can see, they mention a lot. We eliminate the intermediaries, and that shows that they are vertically integrated, and they are reducing cost in every single step. And another thing is that lithium is another of those materials that you can find everywhere. And the problem with lithium is that it's difficult to extract, but they managed to do a system using salt, table salt, to extract it, and they got a concession of a mine in the US. That way it's gonna be perfect, because they're just going to extract all the lithium they need for the US, and they will leave the land the way it was originally, but without the lithium. So it's another win-win situation.
Yeah. So it's important to note that there is a massive amount of lithium on Earth. Lithium is not like oil. There's a massive amount of it pretty much everywhere. In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. Like all the cars in the United States, there's like 300 million or something like that. Every vehicle in the United States can be converted to electric using only lithium that is available in the United States.
Discovered today.
What we already know is exists.
People really haven't even been looking.
Yeah, people haven't been trying, because it's just like widely available. So, long-term, new batteries will come from old batteries once the fleet reaches steady state.
Okay, so we just talked about scaling cathode and recycling. All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our half the cost goal, but there's one more section. Take it away, Elon.
So far we've been checking all these 4 steps. The last one adds 12% more cost reduction in kilowatt hour. So we're at 49%. And now we're going to talk about the cell vehicle integration, which is going to integrate the cell into the structure of the vehicle. That's really, really cool.
Sweet. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy, because we wanted a high strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of like does this like potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. So that's a great achievement of our materials team.
That's amazing. So they are producing a one piece of the entire rear of the car engine, and in one piece. And to do so, to achieve this, they had to make their own alloy to produce it, so it works, and because there's difference in temperatures.
So that's a great achievement of our materials team. In fact, in general, we've got a lot of advanced materials coming for Tesla, that new alloys and materials that have never existed before. So you're basically making the front and rear of the car as a single piece, and then that then interfaces to what we call the structural battery. where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure.
So basically, the battery is going to be the battery and the structure of the car all together, one piece.
Interfaces to what we call it the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is absolutely the way things are done. In the early days of aircraft, they would carry the fuel tanks as cargo. So the fuel tanks actually were quite difficult to carry. They were like basically worse than cargo. You had to kind of bolt them down. It was very difficult. And then somebody said, hey, what if we just make the wing tanks, what if we just make the fuel tank in wing shape? So all modern airplanes, the fuel tank, your wing is just a fuel tank in wing shape. This is absolutely the way to do it. And then the fuel tank serves as dual structure, and it's no longer cargo. It's fundamental to the structure of the aircraft. This was a major breakthrough. We're doing the same for cars. It's really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. So it's like, well, how do you really minimize the mass of a battery? Make it negative. Make the battery non-cell portion of the battery pack negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. What we do is essentially, instead of having just a filler that is a flame retardant, which is currently what is in the 3-in-1 battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it also allows us to use to move the cells closer to the center of the car, because we don't have the in the top one we've got sort of all the supports and stuff. So the volumetric efficiency of the structural pack is much better than a non-structural pack, and we actually bring the cells closer to the center, and because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because any kind of side impact has to go further in order to reach the cells. It also improves what's called the polar moment of inertia, which is that you can think of like when there's ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You won't know why, but it just feels more agile.
So basically, they bring the cells together to the center to make the car more stable, and so the center point, the gravity point, is going to be more concentrated in the middle of the car, which will make the car to turn better in the corners.
70 fewer parts. So, I mean, I really think that long term, in any cars that do not take this architecture will not be competitive.
And it's not just.
I really think that long term, in any cars that do not take this architecture will not be competitive. I really think that long term, in any cars that do not take this architecture will not be competitive. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts.
So they, as I said, they touch every single detail of the entire process. They reduce everything. The number of parts in the car, they simplify it to the minimum level, and they're always simplifying. They've been always doing the same thing. And as Elon says, that was not a mistake. I played it 3 times, saying that competitors, if they don't do the same, if they don't adapt, if they don't change, they won't be competitive, and they're going to disappear.
Yeah, so major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
Yeah, at the beginning of the video, I said 76%. Okay, that was way too much. 56% dollar per kilowatt hour reduction is already a lot. It's a lot. But as you can see, there's a lot of things that need to be done in order to achieve this. Okay, I think we'll leave it here, and I'll see you in the next video. Okay, thanks for watching. Bye.